Okay. Should we start? Okay. So if you guys haven't muted yourself, please do that. And we'll start right now. Cool. So hey guys. First, I just really want to thank the people who are in person right here. We got Timbits. If you're hungry, come grab some. And for those who are online, if you want to see my face, you can come to the in-person next time. But still, thank you so much. Thank you all so much for being in the meeting. And I'm pretty sure we're going to have some good time together. Okay, so this is the study group sessions for UTMIS, and hope you guys are not in the wrong room. And today we're going to go through some basic machine learning knowledge. But before that, let's talk a little bit about what is study group and see why you guys are here. So study group is basically an approach from the UTMIS Club for beginner students to learn more about machine learning knowledge. And it's basically based on the Coursera courses named Introduction to Deep Learning. And from that, we'll be providing help on your way to retrieve your own certificate. Yay, certificates! And it's free. It's sponsored by U of T, and so don't worry about the prize and stuff. So that being said, a lot of people have asked me questions regarding how do we enroll, and I just want to make it clear. So if any of you guys haven't got your U of T sponsored Coursera accounts, or if any of you haven't tried this before, so basically there'll be a link in the PowerPoint. If you go to this link, there'll be a join button next to the course name. So like Introduction to Deep Learning, there'll be a join button. Just click the join and log in sign up with using your U of T account, and everything else will follow. If you have more questions, you can just email me on the, yeah, you do. Don't worry about taking notes and stuff. You get this slide, but I will also be annotating on the way. So if you're interested in taking notes, please do. Feel free to do. But the slide as well as the Zoom recording will be available right after the sessions, perhaps today. Our TA, lovely Mindy, will do this job for me. Thank you so much. Okay, let's talk about more about study group. So first, you get to have a lot of fun because we actually have a lot planned for the fall semester as well as the winter semester. So in details, we're going to talk a little bit about neural network. Specifically, this course is all about neural network. Specifically, we're going to talk about multi-layer perceptrons. We're going to talk about convolutional neural network. We're going to talk about GAN. Also a little bit about autoencoder. So all that fun stuff. And if any of you guys are interested in natural language processing, we'll be also talking about RNN. Maybe not ES transformer, but we'll see on our way. So you're gonna have a lot of fun, and we're gonna have quizzes. Of course, not for March, but for the Coursera courses, you're gonna meet a lot of quizzes. They're weekly quizzes, and there's gonna be unit check and stuff. So we're going to be answering questions of those, and perhaps if we had time, we're going to go through the quizzes. And so if you're here in person or in the Zoom, you also get free solutions, which is great. Okay. And hopefully you will understand it, but not just copying the solutions, But we'll see how it goes. Next one is we're going to have general Q&A sessions. I hope that you guys don't ask questions on the spot, because if I don't know the answer, that'll be very awkward, but I will try my best. If you have any questions, just ask me. I'll try my best to answer it. And you can ask questions at the end of the sessions. I'll tell you guys, okay, this is the end of sessions. Or you can ask me questions regarding the slide after I'm done with each slide, just because I have a really linear process brain. Like if you break me off during I'm explaining through the slide, I may forget where I started with. So guys, please do me a favor and ask the questions at the end of the slide, and that will be greatly appreciated. Cool. And you also got a lot of programming assignment for this course. I know it's a lot in order to get the certificate, but I'm not planning to do the assignment in this sessions. But if you guys have coming questions regarding the programming questions, or if you have any bug that you cannot solve, email me. Or if you have like general question about how do I approach these questions, how do I complete, how do I code, that's okay. Send me an email. If you request to a solution of this assignment, I probably will not give you the solutions, but I will talk about how do we approach this type of questions and how exactly do we code. And the request, we do it. The next part is we have some fun project collaboration with the project workshop. So that's happening right after the session. So it's a hybrid. I know it's kind of like a hybrid this week, but one of those is coming because in the Coursera courses, there are actually some of the more challenging project. Like they're from the Kaggle Open project, and you just get a database and you kind of just like code. So if you don't have any ideas about how do you exactly construct a neural network, how do you exactly training, or if you want more tips on the training techniques, you can also come to these hybrid sessions. So that will happen as the study group will kind of combine with the project workshop. And as a whole, we're going to just go through our way and go through the project. And of course, that will not be a free solutions for you guys because this course is based on the Python TensorFlow library. But in the project workshop, the hybrid session, so the exactly hybrid session, today is kind of like we do project workshop right after this study group sessions. But for the actual hybrid, they kind of just happen together. So for those, we're just gonna like go through our way together. But this course, the study group sessions is based on the TensorFlow. But for project workshop hybrid sessions, we're gonna provide the code in PyTorch. Yay! Well, actually, you get to use PyTorch in a lot of future machine learning courses you're gonna take, like APS 360s. I don't know if ECE 241 are using PyTorch too, but it's basically a really common tool that you use. And if you know it, it's more easier for you to get jobs and researches as well. So good practice. But architecturally, they kind of work. Hi, take a seat. They kind of work really similarly. So it's kind of like me giving you the solutions, but you have to craft it a little bit such that, you know, it works. So anyway, cool. This slide means that we're actually gonna go on with the content. But before that, let me just introduce myself and our lovely TA. So I'm Lindy, Lindy. I'm Lindy Zai, and I'm an ECE third year student. And previously, I've done a lot of machine learning projects. And it's on my GitHub. If you want to check it out, you can do that. And I've also done summer researches in National University of Singapore regarding accelerated materials. So it's basically GN combined with CNN stuff, and it's fun. If you guys are interested, you can also check it out. And this year, I'm also TAing ESC 180. Is anybody inside here? First year? Yep. Oh, cool. You might see me in your practical blog. Okay. If you have any bug, find me, send me an email. I'll debug for you. Okay, cool. That's my introduction. And hopefully we're gonna have a really fun year. We're gonna have approximately about 12 sessions. If you guys need more, we can add more. If you guys think 12 is too much, we can absolutely reduce it. But I guess it's all about you guys. So this is our TA, Mindy. Introduce yourself.
Hi, I'm Mindy. I'm an EC2T5. I did machine learning over the summer too in research for like a year, and it was actually remote, and it was at UBC, and I had to do it like biomed, so it's like human.
Ooh, okay, so cool. Cool. And without further ado, let's just we're gonna give a so if anybody can mute yourself, please mute yourself, please. Let me see if I can do that. Okay. Maybe they already done it. Okay, cool. So this course is all about deep learning, and today we're just gonna give you a really subtle, really soft intro towards it, and we're not gonna include too much math, but just a little bit high school math. But in future sessions, we probably will dig deeper into the math architecture, such that you guys understand everything about neural network, not just how to use functions in TensorFlow. Cool, but we'll also include code snippets such that everything is crystal clear. And if you guys need more, for example, if you guys are more interested in the coding side, but not too much about the mathematics, I mean, who like math. So if you're more interested in the coding parts, just send me an email. Maybe we'll talk more about the coding in the next session. So it's really flexible. And without further ado, let's actually start. I'm so sorry for the long intro, but let's go. Okay, so I believe anyone right here have heard of the term machine learning, right? Does anyone want to share their insight about like the definition of machine learning? Somebody want to try to define it, or just maybe say, what do you think? Okay, go.
Data and like a program can learn from data like a pattern, and then the pattern you can predict new outcomes based on
Yeah. That's definitely a type of machine learning. Yeah. So he mentioned two really good points. First, we have to have enough data, right? Data is the basis. We have to have them in order to, like whether it's producing predictions or classifications or even, generate new stuff like GN network, right? We have to have those data. So that's the base. And another thing, what's your name? Prashant? Okay, cool. So Prashant mentioned another really good point, which is the algorithm learns. So the formal definition is that it's basically artificial intelligence that automatically adapt with minimal human interface. So if you guys have coded before, the code right now, without taking any machine learning approaches, is basically you producing kind of like a standard code automation process for, like some sort of task. But it's really not too flexible. You may have like different case considerations, but it's working on one task and it's not going to improve itself if you're not going to told it to do so. For example, if you have, does you guys know what is tic-tac-toe? Right? If you, for example, I want to code a bot that can beat everyone in tic-tac-toe. But I don't know where to start. So I basically, my bot algorithm is just putting stones on the board like randomly. Well, obviously that's not going to perform too well, right? So we can maybe try to use other algorithm to help us win about for the game, such as like minimax and stuff. But using that, it's you to improve the performance of the algorithm. So it's you trying new other algorithm, try to improve the performance of your tic-tac-toe bots. However, for machine learning, if you guys have heard of reinforcement learning before, it's just something that learns itself by penalizing its failure and awarding its, I guess, success. It will be able to improve as time passes, and also with enough data, right? Cool. So hopefully that made it clear what is machine learning. But the course that we're gonna especially talk about is deep learning. So it's not too different from machine learning because deep learning is actually a subset of machine learning, because machine learning is a really broad term. It includes many other algorithms like random forest and stuff. But deep learning is, if I have to find out one keyword about it, it will be neural network. So I guess you guys have definitely heard of this term in many places. It's used basically everywhere. And it's very commonly used, and I think it's really good tool to learn. So specifically in the following 12 sessions, we're gonna work with a different type of neural network. But first, we're gonna build the base. So today we're just gonna talk about component of the neural networks, and the following we're gonna talk about how to update the weights in the neural network, and then we're gonna go through different type of neural network that's good for different tasks, because it's just different network are good for different tasks. It's just like, I'm so bad at English. Maybe someone is more better at English than me, right? So we're gonna learn all of that fun stuff. But in order to make you guys keep attending these sessions and maybe have more interest towards machine learning, I provide some example of deep learning neural network. So let's say we have this is not a neural network by any means. This is not a neural networks. It's just pictures. So these are actually data. But what we want to do with it is that we want to classify it. So we want to say which one is Chihuahua and which one is Cookie. For me, if you just give me 0.5 seconds looking at this graph, my accuracy is not even 100%. So if you can code a bot that can achieve 100% accuracy for these type of data, congratulations, your bot beats a human, like me. So deep learning project, machine learning project can do all of those fun stuff because they can take this and basically classify it. And that's kind of one of the very first project that we do, is that we're gonna classify different type of diseases according to the X-ray pictures. I think that's one of the very first project workshop collaborations, and it's going to be a really fun project. But it worked kind of similar to this one, but this one is more fun on the display, so I put it there. And if you guys actually have some basis with machine learning and want to experiment with this, I actually attached the database for this, which is at the link right there. It's a GitHub database. So if you guys want to make a classification project yourself to classify cookies and Chihuahua, that's the database. Go for it. And I believe you have also heard natural language processing. And one of the most common uses of natural language processing is like translation. Of course, we have more like Series, you use Series every day. And that basically convert your voices to some sort of embedding and then translate it to, text. In this case, it's going to work with English and German, and it's translating from German to English, but apparently it's making a mistake. So you also are going to learn about how to improve your algorithm to avoid this type of mistakes in the courses, because that's called like training technique. You're learning to look at the curve and how to avoid the common, mistakes and stuff. And but this is just one of the like downfall of Google Translate. So what's happening over here is basically at the conversion of different word embedding, that's there's some sort of mistake there. The machine basically confuse itself and translate to the wrong embedding. Cool. And does anybody know what is this? It's a type of object detection. So it's cosmetic segmentation. Maybe you guys have seen live of, like when you look at the camera and you saw like a square around your face. So it basically tells that where's your face in the pictures. this is an upgrade version of that. And this is commonly used in the auto driving cars. It's cosmetic segmentation. So how it works is that it basically look at each pixels in the image and says, okay, this pixel belongs to this object and the others don't. And as you see, usually we have big bounding box. If you have heard of the YOLO algorithm before, so you only look once, that basically put big bounding box in the objects. But this basically precise to the object detection to a pixel level, so this is far more precise and far more interesting than that and far more difficult. But if you guys are interested in auto driving, computer vision, go for it. This is just a sample deep learning project. And whoa, so handsome. Okay. Okay. So this is a GAN project, a generative adversarial network. So how this work is that as you can tell, if this picture is not included in this section, but like instead I kind of just show you, look at this picture. You might ask me, what artist, right? But this is actually a machine learning generated product. You basically cannot find any like flaws in it. It's a perfect picture, right? And it's really good looking man. But how it actually works is that you have the if you go to, I actually attached the website over there. It's completely free. You can generate your own character. So how to work is that it's gonna take multiple source pictures, and it's gonna use those as the basis and combine the characteristic and generate a whole new human character. And you can also generate dog. I think I didn't really check that out, but they did a really good job on this. And you can also adjust like different factor like races, age, and facial expressions. And this is really something, right? And you guys are also gonna learn something like this in the courses, because we'll also talk about how do you generate new data from the existing data, and how do you produce like maybe not as good product as this, but how do you produce interesting new data. Okay, cool. I noticed that I'm repeating myself. Cool. So actually now we're gonna dig in some actual stuff. This is so this sessions is gonna focus on the first half sessions, half knowledge content of the first week classes on the Coursera. So we're actually not getting into the back propagation or the weight updates parts. But for here, today we're just gonna talk about what exactly is a neural network and how do we connect each other, and how do we use the simple math to allow the classification or like regression task that I can do. We're not going to talk about how do we make it become better, but we're going to include that in the next sessions. Let's say also involve some more difficult math. I don't want to make the first sessions more overwhelming as it is. Cool. So on this left side, it's a neuron, and actually this is not called perceptrons. This is actually the base of a perceptron model. But on the left there, it's a neuron. On the right there, it's also a neuron, but in terms of neural network. So how they work is that how your neuron works is basically taking an input and it kind of like processes across the synapse and dendrite. I didn't take bio courses, so if I really ruin this, please forgive me. But it's gonna process the original input of X naught. And so if you look at on the right side, I don't know if you guys can see my mouse over here. So if you see the X naught, that's basically the input. That's the input signal in terms of like your neurons. And by processing across the synapse and the dendrites, you're basically timing a weight to the X naught input. So you are using some sort of weight. So W naught, that's your weight. And you're timing them together to adjust, I guess, the density or the how do you say it? Intensity of your inputs. So it's basically like you multiply X naught with the W naught, And now you have a combination of W naught and X naught. I know that's so repetitive, but that's over here. So when you time the weight, the weight multiplication is really important because that's how you adjust the so let's say you have 3 signals, but one of them is more important. Or in order to let's say if the 3 inputs stand for 3 characteristic of a human, and you want to specifically identify you want to specifically emphasize one characteristic of the inputs, you might want to put more weight on that. And we're going to talk more about how do we prevent the false weights that overly address one characteristic, but that's coming later. So as you see, we have multiple input because we have X naught over here. We also have X1 and we have X2. So there's multiple input as the neuron also have multiple dendrites, right? And so it takes multiple inputs and process it in the cell's body, which is, that's okay. Yeah, sit down. And it's basically a summation of a linear function. So how does this linear function work is that it's timing the different weights. So each dendrites over here have different weights. So this is W naught, this is W1, and this is W2. It's gonna multiply to different inputs, and by adding a constant B factor, this B basically, if you see this in your function, AX plus B, everyone has seen it, right? What does B do is that it enable a vertical shift to the function, so that your function is not always sourced from the origin, right? It just used as an adjustment factor over here, and so we're just simply summation it. We're just basically adding them together, adding all the process input together, and put it through the F, which is an activation function. We're going to talk about what exactly activation function do and why we need it, how it did it in the later part of the sections. But so far, just treat it as some sort of mysterious box and process the summation and output the next input for the next neuron. If not, if this neuron is the final neuron that we have, the output is the final output. Is that clear to anyone so far? Does anybody have the confusion about this part, the math? Good. Do we have any question on the chats? Let me just check. Okay, just a general question. What made you choose this Coursera course for this program? Is there a unique aspect or feature of this course you find it useful? Is there another machine learning course on Coursera is enjoyed? Yeah, there is the reasons. Okay, I guess so. First, this course is actually really well structured for me because we actually have researched quite a few Coursera courses, and this is the course that we found in the limited resource that we have. This is the best one because it basically really dig from the mathematic parts. Like it provides a really clear insight of what exactly is neural network and how we can successfully construct one using some of the training techniques. So I think this course is crystal clear in the limited time that it is given. And another reason I would choose this course, if I'm being really honest here, is that it's a U of T sponsored course. The other course, because it's too popular, I think it's really expensive. That U of T didn't sponsor it. This is sponsored. So yeah, that's my honest answer over there. But you will get as much as the other course offered you. Maybe the other course might include more like transformer stuff, but after learning the basic over here, you can go all over the place yourself, and it is it's quite amazing. Yeah. And for project work on Coursera, I think you should be having your own project in order to have separate submissions towards. Okay, that's okay. You guys already answered it. Okay, cool. All right, so seems like nobody have question regarding this slide, and I guess we'll go to the next one. So I know oh, go ahead. Yes, right after the sessions, if you go to the website, this slide will be published over there. But I will be annotating across, and those will not be posted. So if you want, you can just like keep note or something. Maybe next time I'll keep an annotation on there, just because I don't have any like recording devices this time. The annotation will likely be cleared after this, but the recording is always there. We also have the Zoom recording, so if you want to annotate it after you get your PowerPoint slides, you can also do that. Okay. I know I said I'm not going to talk about any of the weight updates, but I think this is quite essential for us to understand why we're connecting neurons together, because I think this is quite important for us to construct like decision boundaries. But this is really simple math, and this is nowhere clear. This is nowhere close to the actual weight update process, because that involves more calculus and more complicated math stuff. But so far, we're just going to use a really simple example to see maybe how we can award the success and maybe penalize the failure. So this is called perception rule in the courses. I did not learn this in my course, but it's called perception rules. I'm learning with your guys. So what it does is that it have a WJ, which is the current weight, and you want to penalize the failure and award the success. So the YI hat over here is your predictions, is what is the outcome from your algorithm, and the YI on the right side is actually the true label. So they're comparing those two inputs by subtracting it to see whether it's overestimating or underestimating, and that's how you define whether, like, that's how you decide in what direction you need to change your weight. So if this is not a good result, you don't want to emphasize your failure, right? So you have to use the subtraction to decide which direction you're actually changing it, and you have to do it the right way. You have to follow the right trend in order to update the weight. And the alpha over here is just kind of like a delta factor. It's like, because if you made a wrong update, that will for sure happens, because there will also be like outliers in your data. That will for sure happens. But you don't want that to make a huge impact. You want according to probability, right? There's not going to be a lot of outlier. So you want the right adjustment to accumulate, and you eventually will have some wrong adjustments. So you need to adjust the alpha factor, which is called learning rate later. So it's basically what little step you take in order to update your weight over here. So just treat it as the delta factor, and yeah. And the Xij is just the input, I believe. So let's give in a really simple task over here. So we have a bunch of blue dots and a bunch of red dots, and we want to classify the blue dots with the red dots, okay? And we given the key that red is -1 and blue is +1. So in this case, blue is the positive case and the red is the negative case, okay? And if I just gave this to you, you probably can just draw the line between the lines. But machine, it doesn't start that way, right? We may have something like this in the beginning. Usually for your machine learning input, if you're not transferring your learning, which means that you don't have architecture basis, you're just basically starting somewhere random. You're just going to initialize a bunch of random noises at your initial weights, and then you try to make them better. That don't always happen. It's kind of depend on luck. If you try with different hyperparameter, it will eventually comes to you. But you have to find your way to update this and make this a perfect classification between the blue dots and the red dot, right? So in this case, we decided to use the following rule. So first, we're going to cycle through the training instances. That means that we're going to go through all of those dots. There's not a lot of them, but that actually happens in your training process as well. So your program have to look at your training set and actually go through every single one of them in order to let them make accumulated impact on your overall network. So you have to go through all the training instances. And the second one is only update the weight misclassified instance. So for example, in my decision boundary, so it's the red line over there. And this decision boundary that I draw on the screen over there is not perfectly classifying the blue dot and the red dot, but we're only updating weight on the misclassified instance. This don't always happen in real life cases because we realize in order to accelerate our learning, we usually tend to do both. So we update on the W on misclassified instance, but we also update it on the successfully classified instance, but just in different directions. Later, we're going to talk about what exactly is gradient descent and how we exactly do it. But in this case, because this is such a simple example, and one important reason that we don't update on both is because we don't want to over adjust the curve such that it was originally correct. And once you adjust it, because it's successfully classified, it go over the boundary. So because this is so simple, we kind of just update it on the misclassified instance such that it works. Anyway, and the third, if instance is misclassified, we have the following rules. So if an instance is positive classes, which is the blue dot. So if the blue dot is classified as negative, so basically it's saying if the blue dot is classified as the red dot, or if the blue dot was one, as you can see on the screen here, if this one single blue dot is not, like classified with the other blue dots, then we say this positive class is misclassified as negative. In this case, we're adding the blue dot's direction vector, not direction vector. We're adding it's direction vector. We're adding the direction vector to the W, which is the vector of this decision boundary in order to adjust it. I'm going to demonstrate how do we exactly add it. And if the instance is negative classes, so if the instance is red, and if it is misclassified as a blue dot, then we just subtract it from the weight. It's just really easy vector math. For the first year students, we probably have already talked a little bit about vector before. Yeah, go ahead. Yeah.
Alpha is the plane that we're
In this case, we only have one vector variable, which is the W. We don't have so in this case, because this is such a simple task, we don't have many inputs. So essentially, we only need one variable, which is the decision boundary. We're only adjusting that to kind of just tilt it and say it's not specifically saying that on the left side it's going to be blue, on the right side it's going to be red, but instead it's just saying like if you look at the graph, it's just saying that if the blue dot is not belong to the other dots, like if you see the one specific blue dot does not belong to the majority on the other side, we kind of just penalize it. This is not a really formal proof of weight updates. So there are some flaws in the logic, especially this is kind of like a visualization of a clustering algorithm, but they're using this in the Coursera example as an I guess a really brief intro to the update of the weight. So don't stress too much about the two variable, which is blue and red. don't think it that way. Just kind of think this blue dot belongs to the majority of the other blue dot, and does this two, I guess, red dot belongs to the majority of the other red dots. And especially if we think about it, if we kind of just tell the graph, it's more like if we adjust this way and more of the blue dot will belong to the left. It's kind of like intuitive in this case. It's not a really formal mathematic proof, but it's just a simple example. So yeah. Does that answer your question? Not really, I don't think so. Yeah. X, Y axis. Oh, you're asking this question. Sorry. Sorry. Actually in this case, X, Y doesn't really matter. It's just a plane that basically shows you where your dot is. Yeah. It's not X is the input, Y is the output. It's more like a plane. It's like, you have a map, you have north, you have the south. So it's just kind of like a indicator for you to know that where exactly is your dot. Because if we don't have these axes, it kind of just all over the place. And these axes are used for us to calculate the vectors. So the directions that exactly where the decision boundary is pointing to and where the point of the dots land. So it's not using as input and outputs. Does that make sense for you? Maybe. So I just use it as like location indicator. Yes.
Like here, like you say that W equals W plus XI.
Mhm.
XI is like the vector of that point, right? Which is outside the line.
Yes.
And
Yes.
then
Yes.
you add the vector to the W vector.
Shifted. Yes. I will demonstrate how exactly do we do it. Right now. Does anybody have questions regarding this slide? Cool. Let me check the chat. Okay, no new questions. So we're just gonna continue. Oh, actually, wait, what? Did anybody delete my slides? Okay, that's okay. I think I do have some repeated slide over here, but that's okay. I will just annotate it. How exactly do I do it? This, okay, that's good. I'm just gonna draw the screen over here. So let's say that we want to update this misclassified positive instance, in which can somebody answer me? Do we add the xi, which is the dot's direction, or do we subtract it? It's we add it, right? because in this case, if we're only looking at the blue dot over here, we're misclassifying the positive blue dots with this bunch of red dots, right? So if we're looking at it, the direction vector of the blue dots, it's something like this. Whoops. Cool. So is it still there? Yeah. So that's the direction vector of the blue dots. And as soon as we see the current W was over here, right? It's perpendicular to the red decision boundary. So how do we add it? Is that we kind of shift it and we kind of shift it upwards and let the head of the W direction connect with the tail of this direction, the blue dot direction vector. And then it forms something like this. Let me just change the color. And it forms a new, maybe some other thing is too close to the red decision boundary. So, and it form a whole new decision boundary over here. So if we are going to draw this the new decision boundary, which is using the update W, the new decision boundary will be perpendicular to the new green vector, which is just going to be something like this. that's basically kind of, it's a way of update. And the reason I mentioned this case, I don't think this is a really good example of how you update weight, but this is indeed included in the quiz. So I'm just gonna I'm just gonna kind of go through this brief examples such that it become clear in your quiz questions. We're also gonna go through some of the quick quiz questions later, but yeah, that's basically one simple way of an example of how do you update a linear rate. Yeah. In this case, yes, because previously, let me maybe see if I can. Yeah, previously we see that in the cell body over here, we add the B factor, right? And it's the B factor that allows the linear shift, the linear vertical shift of the overall trend. But because we don't have the B factor over here, we kind of just ditch the B factor to make this a really, really simple yet confusing example. It always goes to the origin, but only in this case. In the actual case, if you add the B adjustment factor, it will not be same as this. So yeah, in this case, because we don't want the curve to go all over the place, and we only want to rotate the decision boundary in order to allow the classification happens. We kind of just say, okay, go through the origin. Let me clean up the screen over here. Do not how to do. Okay, clear outline. Okay, cool. So this is what's in your network. This is what's in your network. It's basically each of the dots, because there's no connection on the left over here. The three green circles are basically the inputs. There are some sort of inputs that you put to the network, and by going through the computation of the connections in the middles, is going to come out with one single output. Sometimes it came out with multiple if you want to use like contrastive loss, but like in this case, we're only looking at the most simple examples, which is only output one red circle over here. So each of the circle that you see over here is a neuron, which we just talked about. It has some sort of inputs, which is the input signal over here. In the middle is neuron. These are the inputs, and this is the outputs. In the middle, the blue circles are exactly the neurons. So they're taking input connection, which serves as the input to which serves as input serves as inputs, and by adding all the inputs, which you can see that there's multiple input connections, right? By adding those inputs and adding the B factor and then adding an activation functions, it's going to eventually output one value. But this output is then served as input to the other neurons. So it's layer by layer and layer by layer. So you may want to ask the questions, why we have so much layers? Okay, so I guess a very easy example is that, let's say that we have, I'm just going to draw on the screen over here, okay? Let's say that we have a Cartesian plane over here. And we have one trend over here. If we have dots on each side of the decision boundary, we can of course classify it, right? Then what about when we have, for example, three type of for example, if this is circle, and we have like squares, and we have like maybe stars and something like that. What if we have three inputs? Then we need two decision boundaries to fully classify it, right? Can you do it with one linear curve? You can't really do that, right? You need multiple decision boundary to enable more classification to happen. And if we only want for example, this side and this side, we would also, it's very clear visually that you also need two decision boundary to kind of just like separate the middle part out. This is actually XOR gates. And you would need multiple layers to enable this. Is that clear? Why we need multiple layers? And sometimes we might need more than 2 layers. Sometimes we have like 16 layers, and it goes deeper. That's why we call it deep neural network and deep learning. Yeah, go ahead. Yeah, sure, for sure. So let me just maybe do this more slowly and maybe with a better explanation. So let's just say using the previous example over here. We have a blue dot along with the red dot, right? But we can like fully classify these two type of dots using one linear trend, which is the red line over there, right? By just tilting and rotating the decision boundary, which is the separation line, we're able to do a full binary classification. But what if when we have 3 type of object that we want to like separately classify? For example, if we have like, whoops, that's okay, we can use this slide. Draw, sorry. If we have, okay, sure. If we have these green dots and this blue dot, and let me find maybe another color, red dot over here. Can you do it with only one curve? You need multiple curve to put multiple classification to separate these cases, right? You need, and this is what I mean by multiple decision boundary. We need multiple separation lines for us to see that, because if we only have one, we can only classify like 2 type of objects. And sometimes if you have multiple objects to classify, we might need more to form the decision boundary base. But that does not mean that you have like, you have 3 things to classify, you need 3 layers. You have 5 things to classify, you need 5 layers, because it doesn't work that way. Yeah, go. Yes, yes. Actually, when we later goes to the convolutional neural network, you can see that each layer kind of just, we will have different kernels, and we will use the kernel to use each kernel to identify a specific characteristic or edges or characteristic of an image of a target. So we can consider it that way. Yes, go. Sorry, pardon your question?
Generally better to decrease the number.
You made a really good point. So it's the engineering decision that you have to make, right? Sometimes we have really deep fully connected layer like this. Your architecture will have way too much parameter to go through for a large database. In that case, you have to say, okay, what should I do to increase our algorithmic efficiency? Usually we have other way to do it. Usually we have like drop off, and we also have other smart ways to increase the efficiency of the algorithm. But in this case, because we're looking at the fully connected neural network, and also because the example that I given, it just classifying 3 type of dots, it just come naturally that we probably need 2 layers. But he really made a good point. We sometimes need to, we want to use less layers as much as possible, just because training always take time. Sometimes my laptop is just running like 24/7. It takes 5 hours to train 30 epochs. It just worked that way. You have to go, because we have to go through every single training instances, right? As we mentioned before. So it's a linear process, and we want to reduce the parameter in the network as much as possible to enable the fast training. Yeah. And this is what they call a perceptual model. And because we have, yes. You can add more. I'm not sure if they add value to your architecture. You can always add more. Yes. Yes. As you train more your network, if you add more and more and more, essentially you will not see an increase in your accuracy, because if you have more, they're eventually just gonna overlap, and it's just gonna increase your training time, but not increasing your training efficiencies. So you can do trial and sometimes training neural network. It's just
what chopper do you want?
What do they have there?
someone is not muting themselves, but yeah, okay. For the multi-layer, because we haven't talked about activation function and we haven't talked about what is nonlinearity, so far, what will happen is that using the 3-dot classification example, if you add more layer, eventually the decision boundary will just get really close to each other, but they form a single one, or multiple of them doesn't really classify different objects. So it's just increasing your training time, but not your accuracy. Okay, and this is a class example that they gave because they want a difficult shaped decision boundary. So let's say that, so what they mean is that they only want data in this area. Then you see the reason that we might need multiple decision boundaries, right? Because we probably cannot define this weird shape. Is this hexagon? It's pentagon, right? It's a pentagon. So we can't really form a pentagon using one line, right? That's why we need multiple linear decision boundary to kind of just like add the summation together. And this is where you see the adding process, and we kind of put it there and bound it. And that's why you need multiple neuron and maybe multiple layers. Yes. Okay. This is just an add-on to the easy 3-object classification example. Is yeah. So that is basically what you come out with. This is that one line does not do the job. Yeah, go ahead. Sorry, pardon? Thank you so much for mentioning this, because I'm actually going to talk about activation functions right now. So linear boundaries, what we've seen with it is that, first, let me clear off the annotation. Okay. So the reason that we need this activation function is that, you know, if you have multiple linear functions, they're eventually just going to combine into a huge, like big linear functions. It does not have the non-linearity. So the function kind of just act like a steel pipe. It's rigid and its shape doesn't change. So let's say that, let's ignore this slide so far and just look at this. Let's say that we have this one curve over here. It's a linear curve, right? And we want to use this to kind of avoid all the objects on the way. So we don't want it to cross with the object. But a linear curve can do that because it's a rigid metal pipe. It kind of acts that way. It's not water. It doesn't flow. It doesn't have the flexibility to change its slope and stuff. That's why we add activation functions. So after activation functions, we're able to kind of just like craft the curve and make the decision boundaries essentially more flexible. When sometimes when you want to, for example, if you want to produce a sine wave shape, can't do that with a linear curve. For example, if you want to do a regression task, so basically producing a curve that fits the trend of the data points, linear curve doesn't do it. If you have a sine wave, you need to have sine wave train, or you can use other type of polynomial train to approximate it. But absolutely, you cannot do it with a linear train. That's why we need the activation functions. And you will see that eventually in a lot of the every neural network have activation functions. They use the activation functions first. They bound the outputs between 0 and 1, sometimes between -1 and 1. So they use it as a boundary first. And then they also add the most important reason why we add this is not because we want to bond. The most important reason we want to add this is that we want to shape it not as a linear curve. We want to add non-linearity into it. And this is exactly the reason why neural network works, because it's not just a set of linear decision boundaries. So these are some common activation functions exist on the market right now. It's just sigmoid 10H. Usually people use ReLU and sometimes leaky ReLU to enable the incoming negative values inputs. Yeah. Does this kind of make sense to you guys? Okay, yes. It's not using any activation functions. It's just a linear boundary. So let's actually go back to this neuron structure. So the activation function is actually adding at the end of the cell body. So it's after we sum every single linear input, we add activation functions. But for our like blue dot, red dot examples, we kind of just use an AX plus B type of decision boundary. So as you see, if you have to say what is the F, the activation function, it will be a 1, but that's not called an activation function because the purpose of activation function is to make the linear decision boundary non-linear. But we're using linear boundaries. So this is actually the blue dot, red dot example is not a neural network example because all decision boundary is linear. So in this case, if we apply an activation functions, the curve might go something like this. I don't know. It could be something like this. Yeah. So it's more flexible. It allows more like precise classifications. And yeah. Does that answer your questions? Yeah, go ahead. You can. In fact, because every layer, sorry, let me see. In fact, every layer in the middle, you always have to process the inputs, right? You always have to process the outputs at the end of the neural right here. If you look at my mouse, you usually apply the activation function right here. Usually one layer, if you use PyTorch or TensorFlow, they usually use one activation to keep the consistency of the same input, in the same layer. So you could use ReLU over here and maybe sigmoid over here, but it's usually consistent within the current hidden layer. So one layer is called hidden layer. Yeah. And the number of neurons in the middle is called hidden units. Yeah. And yeah, that's essentially what is an activation functions. Do you guys have any questions regarding it? If not, we got to quiz time. JK, actually no quiz, but we do have quiz, okay? We do have quiz, but in this case, it's not for Mark. We're gonna go through the first quiz of week 1, and it will be really fast because the questions are really easy. But we're just gonna go through the questions and provide the solutions along with the questions, and maybe check your understanding on the stuff that we talked about. In the future sessions, we might include quiz, we might not include quiz, depending on how much content we have in that 1 week, because this is whole bi-weekly. It's not likely that we can just stuff in very little content in there. We probably need to talk about more about like assignment and focus on the more important stuff. So if you guys have any questions regarding the more difficult mathematic or knowledge content, send me an email and I'll make a decision to kind of like just cancel the easy part and kind of focus on what people want to talk about. So, and if you guys want to talk about assignment, send me an email. We'll talk about assignment instead of the quiz. But this, because first session's just gonna go with quiz, and Mandy will read the questions and give you guys a few minutes to think about it. And because we forgot to do a Kahoot this time, we're just gonna raise our hand and see what option you want to choose. But yeah.
Okay, so which of the following logical operations does the following perceptron represent? Note that x1 and x2 are binary. Does anyone have an answer?
I think that would be way too fast for someone to answer that. Probably
No.
given can you make it bigger? Oops. I mean, we can make it bigger. Well, quiz. Okay, actually quiz. Okay.
Okay, wait 1 sec.
Whoa, okay.
Okay,
Okay,
how do we do this?
that's okay. I think that's good enough on the left side. Can you see it? I mean, it's just 4 options. Whoops. Okay, that's okay. That is good, I think. So it's basically 3 inputs connected with intermediate weight. And maybe I need to explain a little bit about what is OR, NAND, and XOR, right? Does anybody know what is OR, NAND, and XOR? Go ahead.
Just one has
Uh-huh.
X forward is only one.
Whoa, okay. Okay, yes, that's fully correct. Yes. So it's to repeat, it just or is if either of the input is 1, it becomes a 1. So in this case, x1 and x2 are just either 1 or 0. Okay. And oops.
I'm just trying to-
Okay, we're just trying to make the picture bigger. And that's okay. And think OR as a plus operation. So if so either input is either 0 or 1. So if you have 1, if you have a single 1, the outputs will be bigger or equal to 1, right? And the AND operation is kind of like multiplying each other. So if either one of the input is 0, then whatever time 0 is 0, right? So it's only if the 2 input is 1, the AND will become a 1. And then it just AND tilde. So it's just the completely opposite of AND. So it's just like after you input it, if it is a 1, then the NAND operation will be a 0. And if the AND operation returns 0, then the NAND operation will return 1. So it's the completely opposite of AND. And XOR is just it doesn't, when 2 input both become 1, then the XOR returns to 0. So it must be a OR. So it's either, it must be for the 2 inputs, they must have 1 0 and 1 1. And that will return 1. Yes.
If you add the base back, so you don't have books actually not out.
Yes. Yes. Has everybody heard what he said? That's okay. I'll repeat. So essentially, what's happening here is that I will annotate over here. So everyone has remembered how this neuron operate, right? They kind of just take the inputs, multiply by the weight, and sum at the cell body, right? So over here, the first step is we have the 1 input in the blue bubbles, and we time that by the weight by negative 2.5. Sorry, I'm really bad at drawing this. 2.5, right? Okay, And the next step is we come to the next input, which is the x1 over here. So we plus, because the cell body y1 does the summation process, right? As we see in the neuron diagram. So we do x1 time this time 2, x1 time 2, and the same thing for x2. Oh my god. Okay. What? Okay. Really? Can I do that? That's okay. I'll just keep it as I'll improve it next time. Sorry about the bad writing. And we're looking at whether this is bigger than 0 or not. So because of the horizontal shift, and we also have the limits because this is logic gate, the input is either 0 or 1. So this term, the maximum value for this term is 2, and the minimum value is 0 because we time it by 2, right? So this term is either 0 or 2. And the same with this term. And for the vertical bias, we have the negative 2.5. So in the only case for this summation to become positive is to have 2. Does that make sense? Right? So that means that both our x1 and x2 have to be positive 1 in order to result in a positive answer. That means, and that's exactly the logic of an AND gate. So this answer will be x1 and x2. Does that make sense for you guys? Yeah? Yeah. Sorry, pardon? Uh-huh. Okay, so let me maybe explain what is AND gate. So for AND gate, it's like multiplying two parameters, and the parameter can either be 0 or 1. So AND gates operated exactly like multiplication. So when you multiply two parameters, if either of the parameter is 0, what will be the answer? 0, right? So in what case, when we're timing two parameter, the result will be a 1. We only have 1 parameter, right? We have like 1 times 1, that will be a 1. If either of the parameter is 0, we will have a 0. That's what AND gate is about. You have to have two positive 1 parameter in order to result in the positive outputs. And exactly that's exactly what this logic expression is about. We have to have this we have to have a 2, and we have to have a 2 over here. That means x1 and x2 have to be both 1 in order for this whole expression to be larger than 0, because this is a negative 2.5. Negative 2.5 plus 2 is negative 0.5. That's still negative. So if we want this expression to be positive, we have to have 2, which is 4, right? 4 plus negative 2.5 is 1.5. That is larger than 0 now. So that will be a positive output. Does it make sense? Okay, cool. Does anyone have problem with this question? Yes. So greater than 0. So it just the summation of different terms, so what I've done here is I basically take the input, time it by the edge weight, and get it and sum it at the y parameter, right? And in that process, the summation, because we have a 2.5 factor here, it doesn't exactly work as logic gate. It just means that if your output is larger than 0, because it says here are binary. So if the output is larger than 0, then it's positive. If the summation product over here is negative, then the overall produce a negative result, which is 0. So like usually, if you guys are computer engineering, or if you guys are taking programming courses, you will see the binary notation, which 0 stands for false, 1 stands for true. So basically that's what's coming here. Yeah. Does that make sense? Yes.
So like, assume that like the value of that like might be
So why we're assuming the value of 0 as the threshold? Just because if we can take other threshold, but the most it doesn't. I know like this question lacks some assumption, like it doesn't say is that we're using 0 as the comparing threshold, but that's just usually the comparing standard for kind of like this type of questions. If it is larger than, so for example, if you have a switches, sometimes electrical switches, sometimes it just work as if you see a little bit tiny current, it opens up. Or if you see a little bit like tiny current, it opens down. So it's not about the exact amount does it have, it's about whether it exists or not. So the boundary for that is just 0. So we're just using 0 for this case. And also it's quite obvious just because we have the 0.5 over there. If we add 2 to 2.5, negative 2.5, it's just negative 0.5. And it just come really obvious that 0 is the boundary. Yeah, and I think we also have, so the quiz one is actually a lot of them is about logic operations. So let me try to clear the annotation. I think you can tell online people to put the stamps. Okay. Minnie make a really good point. She said that the online people can also put stamp on whatever option they want to choose. So you guys are free to do that as well. Wait, how do I do it? Cool. Okay, so question 2 is a true or false question. So the following training set can be classified exactly by a single perceptron. True or false? And those of you online can put a stamp on what you think the answer is. I feel like we can also do polls. I don't know how to do it. We can find that next time. Yeah. Someone put true over there. Okay. Oh, I like the I like the stamp that they're choosing. Cool. Does anyone have their guess already? True? True? Yeah, it's true. Does anybody want to explain why it's true? Yeah, go. Yeah, sure. Whether you did, it's fine. It's fine. Either it's fine. Yeah. Mhm.
So we can like X2 can have like a stronger weight than X1 in this case, and then the threshold value can also be a more value. So then like if X2 is true, like they want to be true as well. If X1 is true, why would it false? That's how I know.
And does anybody else you can check. Yeah.
Okay, I did it.
Uh-huh.
So,
Uh-huh.
so they get one.
Uh-huh.
Why is false? We set the y minus.
Exactly. That will also work. Yes.
So you just pick one position. It's enough, I was thinking second.
Exactly. Both, I mean, all of the answer is correct. And basically, if I'm going to repeat what they just said, there are basically two main methods. One of them is plotting. So if you guys are familiar with Cartesian coords, you're just plotting this point on the coordinates. And you can find one decision boundary is enough for classification for all of these dots. It's just like the red and blue dots example that we given. One decision boundary is enough. And the other method, which is more easy in my opinion, because you don't have to plot it, is essentially just observing the trend of x1 and x2. And we found out that the y is only positive when x2 is positive. That means that we only need to check whether x2 is 1. That's only one checking condition. So that means that we only need one perceptron in order to finish that task. So the question statement is that whether it can be classified exactly by a single perceptron. This is true. And thank you all for the stamp. I'm going to clean it, and you all got it correct. Just a note that the question on the Coursera actually is not the same always the time, like every time. So this problem, the format is stay the same. The value in the table sometimes changes. So if you're just like taking the solutions and you go to the Coursera and just input it, it sometimes is false. So you also need to know how exactly does it work in order to input the solutions. But that's it. Yeah. For the sample that we gave in class, it's true. The next one. Okay.
Okay, so which of the following can be guaranteed to behave as activation functions and are not difficult to train? You can select more than one option.
So these are actually this question is actually for the people who have actually watched the video before the classes. But I guess I mentioned some of the functions in my previous slide about activation functions. Can you guys still recall what I put there? And the online people, you can still put stamp on it. So yeah. No. Okay, go. The boy in the gray shirt. Yeah.
Everything except sign.
Everything except for sine and cosine. Correct. Yes. Yes, that function. Yeah. You know, like the two conditions I mentioned about like activation function. First one is like it's bounded, right? But like for sine and cosine, it's kind of like waving. So if you have like you kind of want step function is bad though. Yeah. So we don't use that. We don't use step functions, but most of the time we just use exactly the hard points. The sine and cosine. The reason that sine and cosine won't work is that if you have a very large input output value, you want to bound it. But if you're using a cosine curve, for example, if you have cosine infinity, do you know where it lands? You know it's between 0, you know it's between -1 and 1, but you don't know where it lands. You want it as when it goes to infinity, you want it to go to one specific limit, not just oscillating like a sine and cosine wave. So the sine wave and the cosine wave doesn't really work. So we don't want the over like the very small value or very big value to be an uncertainty. So we kind of just like want to bound it between this value. And if the value is way too big, we'll kind of just bound it to 1. And if it is way too small, we'll bound it to 0 or -1. Yeah. That's okay. And we will show.
Consider a model is being trained using the perceptron algorithm. Let W be the current weight and X be a misclassified instance. Which of the following statements are valid? So take some time to think about it.
And a tip for this is that we actually kind of just explained how we're going to classify it in the red and blue dots example. It's just a conceptual question, so this is not too difficult. If you go back to the slide, you will actually find out that actually I'll just go through this question because I think this question is not as interesting as the other one. And I think for this question, we're just gonna choose if X is positive. Exactly. Thank you, Cole. Thank you. That's the two options that you should be choosing, because that's exactly what's on the slide previously and on the red and blue dots example, and that is how we go through the perception model. Yeah. And yeah, I think you can move on. And this is sorry, the previous question is pretty like self-explanatory, because if you just look at my previous slide, the answer is just right.
I think it's the same one.
Did I put the wrong example? Oh yeah.
Okay.
Okay. Crap, I thought I screwed up. Okay.
What are the possible hyperparameters that can be tuned for a multi-layered perceptron? Select one or more. And put stamps.
Yep. I have briefly mentioned what is hidden layers and number of nodes in a layer, but I guess it's pretty like self-explanatory. What is number of node in one layer, and the number of hidden layer is just how many layers are there in the neural network. Does anyone want to take a guess? Yeah. Yes. Can I ask why is that? Yeah. Okay. If I'm gonna repeat what he said, he basically said everything except for the weight, because we cannot tune the weight, because that weight adjusting the weight is exactly how the machine learn, how the algorithm learn, right? And that is the part that we have to that we have to allow our neural network to do. If we tune the weight ourselves, there's no difference between neural network and just regular programming. And yeah, so that's the only reason why we can adjust the weight. And for the others, we also have talked about selecting number of layers, adding multiple decision boundaries, and number of nodes in the layer, which is adding different like weights to different inputs. And the activation function, I just show you different activation functions that we got. And with that being said, I think we are just gonna do a little bit of preview of what we're gonna talk about in the next session. So the next sessions, we're actually gonna talk about loss functions. So that's how that's some like more math for you guys, but not like this time, because this is legit how you actually calculate loss and how you update your actual neural network according to this. And we'll actually use some real code snippets as examples of how you define your loss functions, how you calculate your loss functions, and how to do all that stuff. Oops. Did I only put one? Okay, I'm not so scared. Okay, and backpropagation and delta rule, more math. So this is just calculus stuff, and we're just before I was showing you how you kind of just go forward in the network, right? So you basically time the weight to the inputs and you sum it and you put it through the activation functions. This is how you backpropagate. So you take your output and see if it is a failure or it is success. And you take that backward to your network and updates every single one of the weights to your desired direction, I would say. So that's how backpropagation works, and it's just math. If you guys know a little bit about chain rules, that would be good. If not, we will be going through that as well. And lots of code examples, yeah. And optimization intros. Next sessions, we're going to talk a lot about training techniques. So overfitting, underfitting, and batch, maybe not batch normalization, but like mini batch, and this, all kind of that stuff. So yeah, I think, is that the last one? Yeah, I think that is the last one. Cool, guys. That ends today's sessions. If you have any general questions, you can ask right now. For both of the Zoom guys and people in the classroom right now, feel free to ask questions, and